Cool. When you want. Okay. My name is Logan Saether. I'm from Chronologic. I'm a Solidity developer, and I'm going to be talking about what we've been working on for the last few months, which is the Ethereum alarm clock. Okay, so what is the Ethereum alarm clock? The Ethereum alarm clock is an open source smart contract protocol. It was originally created by Piper Merriam in 2015. Piper is a veteran dev. He's now at the foundation, and he has a multitude of projects that he works on. Unfortunately, the alarm clock was one of the projects that fell out of use, wasn't priority for a while. For that reason, it wasn't working. When Chronologic came around and picked it up, what we did was we rebuilt it, got it functional again, built up a ton of JavaScript tooling, rewrote the whole test suite using Truffle, and we've been building a front-end dApp that uses it, and we're hoping to get a lot more third-party integrations involved. So right now we have it deployed on Kovan and pending on the mainnet. So here's a picture of Piper doing the first talk on the alarm clock at DevCon 1 in 2015. So what is the reason for the alarm clock? It's pretty simple. What we want to do is be able to schedule transactions, and we currently have no native way in Ethereum to accomplish this. So the reason for this is because all transactions require an external trigger. So what we want to do is be able to set the parameters ahead of time, say when we want this transaction to happen, and then have guarantees that that transaction will go through. There's various solutions for this that involve just server-side cron jobs. The big value add of the Ethereum alarm clock is that it's on-chain and trustless and uses incentives to guarantee executions. So I'll go into just a few use cases here. The first one, of course, being buying tokens from an ICO. If you're in a different time zone from when the ICO launches and you don't want to stay up until 4 a.m. at night, you can schedule the transaction, it'll buy the tokens for you, and you can transfer those tokens out. Any kind of routine call can be scheduled using this. So if you have a rent payment, you can fund a wallet for 6 months, a year, and then have that wallet similar to a pool transaction if you schedule all those transactions for the first of each month. In general, it unlocks a lot of possibilities with smart contract integrations. The EAC Canary is another dApp from Piper, and what it does is it schedules to itself every 2 hours just to make sure the service is working. We're hoping to see a lot of client-side dApps use the alarm clock, wallet integrations, and a really cool use case is the ENS, the Ethereum name system. So right now it involves 2 transactions, a commit and a reveal, and the reveal happens 2 or 3 days afterward. So if you forget to do a reveal, you lose your money. What you can do now is when you commit, also schedule that reveal transaction and not have to worry about coming back in 2 days to reveal. And then run a time node, which is the executioning client. And I'll go into more about that. So right now, what we're focusing on is our partnership with MyCrypto, and we're looking for a lot more third-party involvement here. So we're very open to just getting involved with projects that think they might want to use this service. So for MyCrypto, what we're doing is we're doing all the code, and we're submitting a pull request. And if we might be interested in doing more things like this. If anyone wants to talk to us about it, we have a booth just outside. And now I'll be going into a little bit about how the alarm clock works on a deeper level. So the reason for the alarm clock is that we have two types of accounts on Ethereum. We have the users and the smart contracts. And the smart contracts are unable to call themselves. So the users are the only accounts that have to go through this manual process of creating a transaction, signing that transaction, and publishing it to the network. And what the alarm clock wants to accomplish is to create create smart contracts that can execute by themselves. So the way we do this is we have so a user knows what transaction they want scheduled, and they talk to the alarm clock protocol. They can input these parameters. It deploys a new contract. And then on the other side, we have these executioning clients called time nodes, and these are watching the blockchain for every time a new transaction is created. It'll store it and then execute it once the execution window comes along. So the architecture can be broken down into like 4 main pieces. We have the schedulers, the Requestfactory, the request tracker, and the transaction requests. So the schedulers are the top level of entry point. And below that sit the Requestfactory, which actually deploy the new contracts. And the request tracker keeps all of the addresses in storage. So this is a way we can keep everything on chain. And even though we have off-chain executioning clients, they're always querying the request tracker to see what's stored. This is just another way to kind of organize it. The schedulers are sitting at the top, and all their libraries and Requestfactory is sitting below them. Here's the dependency chart. So there's about 20 smart contracts in total, most of them libraries, and they are all interconnected, talking to each other. So it's architecturally a little complex with how it works, but most of what is going on here is validations to make sure all of the parameters are correct. So the scheduler, it's the top level entry point. There's 2 varieties. So if you want to use block numbers, you can set all the parameters using blocks. If instead you want to use a timestamp, we can offer that as well. So the parameters that the scheduler take, we have the to address, which is the recipient that the transaction will be sent to. Bytes, which is the call data. So if you want this transaction to go to a smart contract and execute a function, you would input the encoded byte data here. And then 8 unsigned integers, which I'll go into right here. And these are what actually the parameters that you want your transaction to have. So, so these are just the same parameters that any Ethereum transaction take. You specify the call gas, the value you're sending, the window size. So this is when you want this. So this is the size of the execution window. The window start. So when you want the execution window to start. Gas price. And then we have a few parameters that are specific to the alarm clock protocol itself. We have the fee, which is a way for any kind of integrations to make some money off of integrating the alarm clock protocol into their application. And then we have the bounty, which is what is rewarded to time nodes when they execute transactions. And the required deposit, which is part of the claiming mechanism. When a time node wants to claim a transaction, it sends this deposit. So let me jump back to this timeline here. So the execution window is when you want your transaction to happen. Because of network properties, we can't guarantee a specific block. So you set a window, and this is a variable. You can set it for as long or as short as you like. A good minimum would be about 10 blocks. So before the execution window, we had the claim window. This is when time nodes can send that deposit and say that they're claiming this transaction and that they'll execute it. So if they claim it, they get a guaranteed exclusivity window at the beginning of the execution when they're expected to execute this. And if they fail to execute, then it does go into the free-for-all window here. And the bounty that they had sent to claim that transaction then gets rewarded to whoever executes instead. So the Requestfactory is what's actually deploying all of these new transaction request contracts every time someone schedules. So what this contract does is it just deploys the contracts. But what's a really cool thing here is that we've recently integrated the clone factory pattern, which there might be a lightning talk going on right now about it. What that does is it, instead of deploying the full contract, it'll deploy this small piece of bytecode, which then just delegate all calls to a kind of like library contract. So this was really cool for us. It saved us a ton of gas. If you have something that's deploying a lot of contracts, this is a great way to optimize your gas usage. So here's the Requestfactory interface. It's pretty simple. This contract really just creates the requests. It also provides some validation on the parameters that are inputted. So usually you want to use a create validator request when creating a new transaction request. If you use the lower level create request, no validation is done, so you might end up wasting gas if you input parameters that don't make sense. And then just functions to check to make sure that this factory is aware of transaction requests. So the transaction request is what actually stores all of the scheduled parameters. It stores the funds that you send it. The funds will cover the gas usage, the value you're sending, and we kept everything in this kind of like isolated, like per contract environment instead of keeping everything in like a centralized place to avoid any kind of vulnerabilities about keeping large amount of funds. Like I mentioned before, this contract just takes all the call data it's given and then delegate calls that. And we've also included a proxy function here. So if you do schedule a transaction to buy assets or buy tokens, those tokens will then be sent to the transaction request contract, and you can proxy call that out to make those tokens actually useful. So here's the interface of the transaction request. there's 3 actions you can use: execute, cancel, and claim. Execute and claim are both time node related, and canceling is if the user chooses to cancel the transaction. The proxy function I mentioned before, and then just a few ways to pull payments and get data from that contract. So if anyone's interested, here's what the proxy function does. It takes the encoded call data and then simply routes that to whichever recipient you want it to go to. So to transfer tokens, it's as easy as just calculating or encoding the data and then sending that to the token contract. And so that's kind of like the scheduling side of the protocol. But on the other end, we have the time nodes, which are actually executing. So the time nodes are client scripts, and they do operate off-chain. But what we have is we're able to create incentives where anybody can run these clients and then get rewarded for executing transactions. So in this way, we kind of encourage people to be running these clients all the time. We think that this is going to be really popular. People will want to do this. So even though it's a client-side off-chain script, we still have this kind of decentralized market that's created over the incentives. So the execution flow, just schedule, and then that'll get sent. So here we see that so when a user schedules a transaction, they'll get back the address for that transaction. They can keep that in case they want to cancel it or check up on it. Time nodes will be watching for the blockchain for every time a new one's deployed. It'll then execute that and get rewarded in the bounty. So with this bounty incentive mechanism, this is how we can guarantee a crypto-economically sound protocol. So regardless of whether that transaction that the time node executes actually is successful or whether it reverts, doesn't matter to the time node, because the time node is going to be receiving the bounty plus the gas no matter what. So theoretically, it's always going to be profitable to run a time node. And although they're off-chain, we should see many different people running these clients. Now I'll talk a little bit about the JavaScript tooling we have. So this is available for developers. And it's a great way to get started with using the alarm clock in your own application. So we have a JavaScript suite that we're calling eac.js. This includes a command line tool to both schedule transactions and run a time node. We also have the time node logic in the eac.js client library, and then we have a lower level library for just interacting with the alarm clock contracts. If you're a developer, I highly encourage you to look into these. We tried to make tools for you to get started really easily. Here's an example of how this looks. So if anyone's worked with Web3 before, I'm sure you have. There's the kind of header you always have to do to initiate it. Then you just pass this Web3 object into the EAC library, and right away it reads the network, and it'll create contracts for that network. So if you're using Kovan, it'll use the latest Kovan contracts. And then it's as easy as just calling the requests. So if you want to execute a transaction, you just call the Requestfactory. You get the latest instance. You can call get request from a block number, and then use that latest one to execute a transaction. So this would be kind of an example logic out of a time node client. And now I'll give you guys a quick demo of the front-end dApp we've been building to kind of make this a lot easier for just your general users. So here's the flow to schedule transactions. So this would be using timestamps. We've made it easier by just putting in a time zone and then converting that to a timestamp on the back end. You can specify the execution window. The information here. So the recipient, the gas price, all the stuff I went over before. The bounty, we've made the claim deposit optional. And then we have Metamask integration here. So after verifying everything is what you set, it'll ask you to confirm, say yes. And then we have this nice summary page. We kind of wanted this to be like a block explorer for future transactions instead of transactions that have already happened. And then from there, users can cancel if they would like to. If not, then they can look into this transaction scanner here. And we've also built a time node into the browser. So to use this, you can use a version 3 MyCrypto wallet. Decrypt it. For this, we're requiring people who use the browser time node to own some of our Chronologic token day. This isn't something that's in the protocol. It's just something we put into the front-end dApp. Sign message there, and then this nice dashboard so to start and stop your time node. You can get the lower level logs. These would be what you're getting from a command line client. This just shows that you're using these contracts at the deployed addresses, and it shows the lower level logic of what this time node is doing. So here it's attempting to claim this transaction request, but we have kind of a randomness built in. So it's saying fate insists you wait until later. So we just have so it's just waiting till later there. And like I mentioned before, we're open to talking to whoever wants to maybe use this. We would love to talk more about integrations and potential partnerships. So I think we have a few minutes if anyone has a question.
Is it possible to encrypt the data?
Increase the call data, or yeah. So the call data is as many bytes as you'd like it to be, and it's like the encoded call data for an Ethereum transaction. So if you want to send a function on a smart contract, you would calculate that client side and then pass it into the scheduled transaction.
It was for the example of ENS reveal. You would not want to put in the clear what your reveal is.
So there's potentially that issue. So maybe not every time you use the ENS would you want to do this. If it's a name that you think might get taken from you, maybe for like some names that aren't competitive, you'd want to do it, but not all. Yeah.
So I saw that there was a field where you could set the gas price in order to get a transaction through under all network conditions. Do you eventually hope to have an oracle pull in from like each gas station where you have like the safe low?
Yeah. So the gas price mechanism isn't perfect yet. We're still like fielding ideas there and trying to figure out the best way to do it. But right now, you set it when you schedule. So it's on a front end side. We want to kind of tell the user what to do there. that's not really taking into account what the network might be like when that transaction actually gets scheduled. So right now, we're saying if you want the transaction to go through, put it with a high gas price, and that way you have a better guarantee it'll go through. But it's definitely something we're looking into and trying to find a better solution for. Yeah.
On the gas costs from this whole process, isn't it possible that the gas costs from just scheduling the call might be more than me actually doing the call on my own through something like a cron job or a task scheduler?
Yeah, so
What are the actual advantages other than, okay, trustless computation?
yeah. So this whole thing tries to target like a standard here of doing this. So using this in like smart contracts or other applications. Using a cron job would be more gas efficient under certain situations there. But what we really want to try to do is get a standard way to do this, so we don't have everybody doing cron jobs separately, and instead we can have a kind of a one global cron job that's running, even if it costs a little bit more gas. Yeah, still have better guarantees that if your server goes down that's running that cron job, it'll still get executed. Yeah.
So let's say in case of paying rent, so ideally, like you said, I can prepay for 6 months and let it be transferred for every 6 months. But what I would like to achieve is like when my rent is due, that's the time I know I have balance in my account. But 10 days from before that, I might not have it. So this transaction is going to require a commitment for paying the
Y-
contract beforehand for the next 6 months. Is there
yes.
any workaround around that?
So there's no workaround for that now. So you'd have to fund those schedules right away. It's not a general solution for pool payments like that. But rather, if you have those funds already, you can just say when you want those to happen. Yeah.
So you have an incentive for the time node to submit the transaction, right?
Yes.
But if the time node fails to submit, it doesn't have this incentive, but does it lose more than not having the fee?
No. So if a time node is running and doesn't do anything, doesn't execute any transactions, it just nothing happens to it. It's just not sending transactions. So it's just not spending any money or getting any money for just running. Instead, what we do is we say if it's sending transactions and it does an execution, that's incentivized. So if a time node sends a transaction, it'll always get the bounty and the gas back. There's never a case for it to lose money. Did that answer your question?
Yeah, I was thinking maybe there is a deposit.
Okay, the claim deposit. Okay, so
No, the time node deposits in the contract to be a participant, right?
no. So the time node is actually just running like a client script there, and doesn't have to deposit to become a time node, but it sends transactions.
Hello.
Hi.
Thank you. So thank you for your presentation. I have a question.
Yeah.
It's about when you lose your private key. Let's say you lose your private key in smart contracts, and then you cannot really call functions anymore and withdraw your money. Would it be possible to have this alarm clock? Like for example, if you don't connect or do any sort of transaction for 24 hours, then you could like the function will withdraw the money to another address. Would that be possible?
Yep. Yeah, that's completely possible. Yeah. That's a use case we've discussed. Yeah. Anything else? All right. Thank you.